Electrostatics of conductors and non-conductors. You already know the specialty of conductors. Conductors contain mobile charge carriers. In a metal, the outermost electrons part away from their atoms and are free to move. These electrons are free within the metal but not free to leave the metal. Inside a metal, the electrons are almost free and it is in a random motion because of thermal energy. So, electric field inside a conductor, even though there is moving charges inside it, then also it is zero. If a conductor is charged, the charge is distributed everywhere on the surface of the conductor. And the electric field is normal at every point on the surface of a conductor. Since the charge is distributed all over the surface of the conductor, electrostatic potential is constant throughout the volume of the conductor and has the same value as on its surface. Electric field at the surface of a charged conductor is given by the equation E is equal to sigma by epsilon 0, and sigma is the charge density on the surface of the conductor. Electrostatic shielding. Let us consider a conductor which has a cavity inside. Cavity means there is no material inside. And the charge is distributed all over the surface of this conductor. Since there is no charge inside the cavity, there the electric field is equal to 0. The potential inside the cavity is same as potential on the surface of the charged conductor. Dielectrics and polarization. Dielectrics are non-conducting substances in which there is no free electrons, and these electrons are strongly attached to the atoms. Dielectrics are of two types, polar and non-polar molecules. Polar molecules, the name itself tells us there is polarity for the molecules. Polar molecule is one in which the centers of positive and negative charges are separated. Such molecules have permanent dipole moment. Usually, ionic molecules are polar molecules. HCl and H2 are examples of non-polar molecules. The centers of positive and negative charges of this type of molecules are coincident. Means it is at the same point itself. So, no permanent dipole moment. Oxygen, hydrogen, etc. Non-polar dielectric means the molecules of this dielectric does not have a polarity in the absence of an external field. When an electric field is applied, what happens to this non-polar dielectric? Let us see. The positive and negative charges of the non-polar molecules displaced in opposite directions and develops a dipole moment. And the total of all these molecules dipole moment together giving a net dipole moment of the dielectric in the external electric field. Dielectric, already you know, the molecules of this polar dielectric is having permanent dipole moment. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation. So the total dipole moment is 0. When an electric field is applied to this dielectric, let us see what happens. When external field is applied, the individual dipole moments tends to align with the field. then there is a net dipole moment developed in the direction of the external field. Or we can say the dielectric is polarized. The extent of polarization depends on the relative strength of the electric field. When the electric field is increased further, more and more dipoles align in the direction of the electric field. That means the intensity of polarization depends on the applied electric field strength. The induced dipole moment in the direction of the field and is proportional to the field strength E. The dipole moment is represented by the letter P. P is equal to a constant into E. The constant is known as susceptibility of the dielectric medium, that is chi E. Let us consider an electric field E0, in which a non-polar dielectric is placed. Non-polar molecules get polarized in the presence of this electric field. Let us see how does the polarized dielectric modify the original external field inside. Inside this material, we can say there is no net charge. This is because the positive side of one dipole is very close to the negative side of the other dipole. So the charge gets neutralized here. However, at the surface of the dielectric normal to the electric field, there is evidently a net charge density. This side it is negative charge density. This side it is positive charge density. The unbalanced charges are the induced charge due to the external field. Thus, the polarized dielectric is equivalent to two charge surfaces with the induced surface charge densities. An induced EMF is developed inside this dielectric, that is EP, in the opposite direction of the applied electric field. The electric field produced inside the material due to the polarization is EP. It is in the opposite direction of the applied electric field E0. So, the electric field inside the material is E is equal to the applied electric field minus the induced electric field due to polarization. That is, E is equal to E0 minus EP.